Rolling element bearings. We talked about the limitations of sliding element bearings, PV value, friction levels, 0.05, 0.1. Rolling element bearings can get friction levels an order of magnitude and less than the sliding contact bearing, simply because you roll. Now, we alluded to earlier and even showed by Hertz contact stress theory that when you have a round object on a surface, remember you push too hard it hurts, there's deformation going down here. So if I draw it real big, what you'll find is that one surface deforms on the other. And if this is the center of rotation, is the center of rotation at the surface or at this radius down here? And this rolling element has been squinched as it's rolling. So as it's moving, it's dissipating energy. That's why it's not 0 for a rolling element bearing, the coefficient of friction. It's finite. Very low, but finite. Still, it being so low, it allows for high-speed rotary motion, high-speed linear motion. It allowed practical trains, bicycles, and indeed, ballpoint pens. The pen rolls with respect to the surface of the paper. Mr. Conrad, way back in the early 1900s, patented a method for assembling bearings, for the deep groove bearing. And if you ever wondered how the balls are gotten into, this is a modular off-the-shelf ball bearing, how the balls are actually loaded into it. The inner ring is displaced to the side, the balls are dropped in, the bearing comes back down, and the balls slowly are then pushed around until you form an even distribution of balls. And then the separator is snapped in to then keep the spacing between the balls. Very important in a high-speed bearing as it's moving. I'll do my little high-speed bearing demonstration here. If the rolling elements are rolling along, they're happy. If they touch one another, they rub. An experiment that you probably may have done once, but probably only once, is as you were riding your bicycle behind your friend, how close can I get my front tire to their rear tire just before I touch and crash? So the name of the game in rolling element bearings is, how do I keep the rolling elements from touching each other? At low speed, it's not so much of a problem. They'll establish a separation distance. At higher speed, the results are very bad for the efficiency of the bearing. Note, one of the methods you can do, and it is done in some linear bearings and ball screws, is a smaller, you have a regular sized ball, slightly smaller ball. Regular sized ball, slightly smaller ball. And this use of spacer balls will help prevent that crash. It acts like an idler gear. It cuts down on the number of balls in the path by a factor of 2, so your load capacity goes way down, but you can deal with much higher load capacity, or much higher speeds. The other very critical part about rolling element ball bearing or roller bearing design is the shape of the contact footprint and its location with respect to the axis of rotation. How is this surface, as it's moving, is there any geometric overconstraint that's going to cause some microslip? It's not necessarily a bad thing, but if it exists, that will affect the efficiency of the bearing. For rotary motion, many different types, ranging from simple ball bearings, or what's called a Conrad design. That was the gentleman Conrad who figured out how to load the balls between the races, all the way up to cylindrical straight rollers, tapered roller bearings, self-aligning bearings, spherical bearings. Why are there so many different types? Well, they have to do with the loads that the bearings are supposed to withstand and the motions that you're trying to control. A simple, what people often call ball bearing, but the ball bearing is actually the ball. Ball bearings can have rotary motion, linear motion. There is no just pure meaning of the word ball bearing other than just the ball itself. Even though some people will refer to, hey, there's a ball bearing. Well, there's many different forms of it. Notice that the load vectors here pass through the center. And if I were to expand that and look real closely, what you would see is the arc of the ball. And then, so the load capacity can be up. Here is the arc of the raceway. And this is not at all typical. This is around 1.5 times the radius of the ball. And it can be as low as 1.1. Again, the Hertz contact equations are used to determine this. So you get a contact patch up here. This bearing, though, has radial load capacity, but doesn't do much for axial load because touching at the peak here is like a neutrally stable point. As you start to load it radially, the outer ring and the inner ring will shift, and you will get an effective load axis like this. So excuse me, this would be if I'm shifting it that way. That leads to the design of a bearing where you say, wow, to get higher axial stiffness, maybe what I'll just go ahead and do is grind that into the structure to begin with. The ball. And here's the outer ring. And the inner ring. And here is the load axis. But when you load it this way, it'll tend to want to fall over. No problem. That just means I'll put another one over here. And I'll just put them back to back. So he puts one load, he puts the other load. And what do you get? You get what's called an angular contact bearing. Whoop. That would be a one to return for warranty work. Really bad warranty work. Let's start over. See, you can make anything work on the board. And what if this was over here? Then I'd have a different configuration. And you see, if you give a mouse a cookie or you give a rolling element a chance to have a surface, vast number of different types of bearings will result. Now this, real stable, what happens when you have the shaft of the system with the bearing on one end and then the shaft extending out, and St. Vinay says you need another support over here, but if this is too stiff, then you get overloading of the bearing. So we will be talking about mounting conditions later on and how to take that into account in terms of doing the analysis of this on the machine. But heading that topic off at the past a little bit, that's where the idea of a spherical roller bearing came in. And this was invented, well, it's still being said exactly who and when, but SKF is the company in Sweden that seems to be where the spherical roller first appeared and was marketed. And with a spherical roller, you've got a roller that is spherical, like a barrel. And this kind of, and then here is the ring, outer ring, inner ring. Here's the center of rotation of the bearing, so everything that's up here is down there. And now the inner shaft, or the inner ring, placed on the shaft of the machine, it can totally free to rotate, yet huge line contact for massive radial loads, and enough of a projected area for modest thrust, or if you want to have very high thrust loads with a spherical roller bearing, you can imagine where I'm going to take and have spheres like this, and then another set of spheres at another angle, where these points meet at a common center, so there'd be very high misalignment capability and very large thrust capacity by using two of them in this face-to-face configuration. The essence of it is that whatever motion you want to enable will always be accompanied by some sort of parasitic motion, that is, or parasitic load, something that you don't want to have happen, but reality says it's going to happen. And because F equals kx, you'll have some parasitic motion. Your job is to figure out what type of bearing can I use, or how do I mount that bearing such that the stiffness is very low, such that the resulting force on your machine due to that misalignment is very low, and hence you don't use up your bearing life. While conversely, figuring out how to select the bearing and mount it such that for the sensitive direction or direction you want to control the load to have the stiffness very high. And then your displacement will be very low given a very high input force to hence achieve the function you desire. The moral of the story is, whenever you find yourself saying, I need a bearing, it's got ball bearing, modest load, but I wish I had a flange on it so I can just slide it in. Something like maybe exists in here. See, this machine here is for a wire feeder. And you can see in here is a modular ball bearing put together with this simple modular framing. What keeps the bearings in place so they don't slide back and forth? If we look here, you can see the bearings in here, and there seems to be some kind of flangey thing here. Well, indeed, that is a flanged ball bearing. And it saves me having to use a lot of parts to mount the ball bearing. Schematically shown like that. So the rolling elements would be in here. The structure to which it's mounted like that. And this is an axis of symmetry, so this is over here. And the shaft comes in, and I've got these couplings, squeeze type couplings in there. On the inside. Shaft through it. And then there was a squeeze type coupling here. And again, here's my axis of symmetry. I'm not drawing it on this side, one, because I don't feel like drawing it, and two, you all have great visual skills now for visualizing if I say flip this part over and make this side symmetric with that side. Bearings called, for example, rod ends have a threaded post on them. Pillow block is typically cast iron or some other structure that bolts down boom, to a machine. You can buy it off the shelf. It has the bearing. Effectively, this part here with the bearing pressed in it that's bolted to the modular rail is a homegrown made pillow block. So you can do all sorts of amazing things with this vast quantity that exists. Again, your job as a machine designer is to be perusing the catalogs, the trade magazines, always looking for what's some new configuration of bearings. And now with the web, you can go do quite a lot too, just going to some major manufacturers' websites. Now, sizing-wise, there are standard sizes for bearings that different manufacturers have come to agree to in terms of the outside dimensions of the bearings. Most of them have similar loads. Where the differentiation occurs is the type of separator, it's the type of lubricant used, and the precision to which the bearing is ground. That is why you have to be very careful when you see, just bearings advertised somewhere, $2 a piece versus, $5 a piece. Is the $2 bearing better or worse than the $5 bearing? It depends. Depends what you're trying to use it for. So just be, cavit emptor, buyer beware. You usually get what you pay for, but $2 may be all you need. We talked about a ball bearing in the context of these little modular elements, but the having of this Hertz contact limitation, even though the groove is conformal to the ball to some degree, the ball being of limited diameter means that even if the groove is close, when I push on it, I'm still limited to this region of contact, this arc of contact. Whereas if I had a roller, and even if I was a little more fair and made the roller of the length of the roller about the same diameter as the ball, I can have many times the contact area for a roller than a ball, and hence many times the load capacity and stiffness. The challenge with the roller, the straight roller, is if I'm to support an axle by a straight roller, I still need thrust bearings to control the position of the axle axially. In other words, if I had a railroad wheel, axle, and another railroad wheel pressed on the axle, and I were to put straight rollers in here between the axle and the car, it would slide side to side. There's nothing to constrain it. You'd have to add additional features to take the thrust. Now, a ball bearing, rotary motion ball bearing, does that, as we showed earlier, with that from a Conrad to the angular contact ball bearing by mounting them back to back. Well, Henry Timken, about 100 years ago, had this really nifty idea. Maybe I can, like an angular contact bearing, maybe I can mount rollers on an inner cone and an outer ring, and they can roll. But you know what? There's this crazy little reality thing going on. For the outer ring, notice that if you're going to mount a roller at an angle, this diameter here you're seeing is bigger than the inner diameter on the other side through the thickness of the ring. So if you just put a straight roller on this ring, it's going to roll out of the ring because this circumference here is longer than this circumference. What Henry Timken did was say, wow, why don't I just use a tapered roller, which didn't exist then. He invented it. And he also invented the way to manufacture it. And that was absolutely revolutionary because it meant you could take railroad wheels and get rid of the sliding contact bearings, which still had this thrust issue, and have very high load capacity with just a couple of simple bearings mounted back to back. Very, very, very clever. Revolutionized the world of railroads. And even to this day, trucks, buses, heavy radial load capacity machines will use tapered roller bearings. If deflections are really high, and that's an issue of the shaft, That's where the spherical roller bearing came in, which also in the early part of the 1900s, where SKF came in. They saw tapered roller bearings come in, very powerful patent, very useful, brilliant bearing, limitations of, boy, it's so stiff. Huh. This was SKF's invention to then say, well, let's make a spherical bearing. That much harder to make, by the way. Now, another type of roller bearing is the needle roller bearing. Mr. Brown was the inventor, and this came about in the mid-1900s, well, 1930s. He worked for Torrington Needleworks here in New England. Torrington Needleworks made needles for the weaving and textile industry in New England, which was very strong, which was going away. So the lifeblood of the company was going away. Guy didn't have any money. His universal joint in his car, he had to replace them. And they had just used sliding contact joints, sliding contact bearings in the universal joint. He's figured, well, they use rolling element bearings to reduce friction in machinery. How can I replace the sliding contact bearing in a universal joint, a very small, tight package with a rolling element? So the lore is that he took some needles home, literally needles, like for sewing machine needles, cut them, fitted them into a sleeve, and replaced them in the universal joint. Fantastic increase in life and reliability in universal joints, essentially allowing Torrington Needleworks to retool as a Torrington Bearing Company, and for many years dominated the field with their very strong patents on needle roller bearings. Needle roller bearing, very long and thin, very small diameter, but so many of the needles in a very small space, you get very, very high load capacity. So in the theory of operation, rolling element to reduce friction is the same for balls and rollers. Both use Hertz contact stresses to calculate stresses and deflections. Both have the same kind of thinking with respect to geometric constraint and the shape of the rollers and the contact surfaces to have your control of the object that you're trying to support, such that, for example, a shaft, 6 degrees of freedom, the rotary degree of freedom you want to let have happen. That's what the rolling element bearing does, but all the other 5 degrees of freedom to support them. How do I apply the bearings to control and provide the constraint on the shaft? It's the same problem we talked about earlier in topic 9 with couplings and interfaces. 6 degrees of freedom, at least 6 directions of contact to support it and control it. Pick your bearings, the mounts, the lines of action. Every bearing has a finite stiffness, F equals Kx. You can then build the model for your machine to predict what not only the stresses in the system are going to be, but the loads on the bearings, where you go back to the ball bearing or roller bearing catalog, determine the load life for the bearing. And we'll be covering that in so much more detail later, including we'll talk about the spreadsheets for it, of course. We just did rotary motion. It must be linear motion too. Indeed, linear motion ball bearings have been around also for decades. But for many, many years, they were around in the context of one structure, rollers, and then the carriage to be moved on top of him. And as shown here, these non-recirculating rollers would go back and forth with limited range of motion. And if things weren't exactly right, this carriage with the rollers or balls would start to migrate and walk. So a whole number of different types of strategies, including just bumpers on the end of travel, to some people putting little gear teeth in there. The moral of the story is, if the parts are very highly precision made, very careful aligned, you almost don't need the bumpers to make sure at end of travel that you keep the non-recirculating roller track engaged without slowly walking itself out. Almost. A good machine will always have it as a safety. Well, that limits the range of travel you can do. And in the 1950s, a gentleman named John Thomson thought of, we recirculate the balls essentially in a rolling element bearing. Why can't we somehow create a virtual rotary motion bearing where the balls are allowed to come back around the top, even when they're only being loaded on the bottom? And that led to the invention of what was called the ball bushing. And what happened that was so revolutionary there is he let the balls roll, but then he added a little pickup finger. And then as the balls rolled, instead of coming end of travel when you're moving this way, right, they would pop out and be taken around and drop down in the front again. And he did that using a round shaft, simply because round shaft was very low cost, cheap and easy to get, very high strength, very accurate, as shafting had always been needed for rotary motion sliding bearings, hydraulic cylinders. So there was an established industry for making very accurate, very strong round shafting. The result was ball bushing. And this is the first type here. But very stiff, such that if the machine deformed, the bearing would get in trouble. And by the way, this is true for any kind of bearing. If the machine deforms that holds the bearings and the bearings don't have the compliance needed, or the structure that holds them doesn't have the needed compliance, you'll overload the bearing. Hence, for example, earlier, the reason the spherical roller bearing was invented. Remember, 1 over ouch equals ah. Whenever you have a problem, if you can't find the component that solves the problem, maybe it's time for you to invent. Well, later on in the 60s, they came out with what's called the self-aligning ball bushing. And the magic of this is, and you'll notice this is a plastic housing, the ball track, or the raceway that is in here, has on the inside, obviously not where the balls are recirculating itself, but where it contacts the outer housing, a bump. So it allows it to pivot, to allow you to have misalignment capability. In this case, the balls are running around the side of the pivot. This guy named Mr. T. Teramachi in Japan looked at that and said, that's really wonderful, really brilliant. You know, these round shafts, if you put the balls on them like this, the bearing has no stiffness in the rotary direction. Indeed, rotate, which some people say it's a feature. But he wanted something that would slide and be able to transmit a torque for a particular type of machine they were working on. So Mr. Teramachi added little wing features and actually put 3 of them for a total of 6 ball tracks. So he invented what was called the ball spline. And this is the recirculating path for these balls. So here, this ball rolling on this track here, if I expand that, you get the ball on a conformal raceway. So you get very high load capacity. for torsion. Let me draw the rest of the housing around that. So this is the shaft. The blue dude is the housing, or the bushing part. These are the recirculating paths for the balls. So this blue structure here would move rolling element linear about the spline, and then the spline here could transmit torque. Well, in both of these cases, people wanted to use these for machine tool slideways. But you see, you're stuck with, when you have a round shaft, if you have a lot of motion, the shaft gets very long and then it gets very soft. In both cases, it evolved what was called the open bushing. Where the shaft can be supported by like a T, making a very long shaft support over its length, but the bushing is open, so it's a little more flexible, but you can pack more metal around it. And the evolution yielded what is called a profile rail bearing. Profile rail bearing has rectangular rail with grooves in it that are ground to be conformal to the ball raceway. And then the carriage has balls that engage that profile rail with recirculating paths within the carriage. And this invention has totally revolutionized the world of machinery and machine tools. I would hypothesize it is as important to modern society as the invention of the original rotary motion ball bearing. Without this type of design here, and indeed I think there's been a lot of people over the years who have worked on and done inventions and pieces of these, but probably it's Thomson and Teramachi are the two real big ones. And then a lot of very brilliant people evolved more after that, don't get me wrong. But in like I said, the 50s and 60s is when you saw this explosion of innovation, and not just, oh, look at this great idea, but the metallurgy, making the rails straight, getting the heat treating right, has allowed now in the 70s and now in the 80s, 1980s and 1990s, boom, an explosion of ability to design linear motion, hence high-speed automation equipment, which has given rise to the semiconductor industry, the modern automotive industry, and now the biology industry with laboratory automation. None of that would have been possible without these linear motion rolling element ball bearings. So it's really, really critical to know about as many variations as you can, low capacity stiffness, when it's used. And the nice thing about all of these things, no matter which one you're designing, you can always just think of them in the following way. You're probably going to guess what I'm going to say. F equals Kx. The bearings will have a certain stiffness, and if you apply misalignment deflections to things, in terms of you force things together, you get a load which can wear them out early. That would be your parasitic alignment force. The bearings are also very stiff, so granted in some sensitive direction you want to have very accurate motion under a very high force by F equals Kx, you can also deterministically make the machine do what you want to do. Same design philosophy and thinking mode for linear motion bearings as is for rotary motion bearings with respect to the type of analysis that we'll do. Can I just use wheels on rails like railroad trains? Sure, no problem. Quite a lot of machinery will use a wheel on a rail. If you look at large extending cranes, you have a wheel and a rail. Rolling element contact stress for a cylinder, you know how to do that. Looking more closely at the ball bushing bearing and the original patent from 1950, let's talk about a little about manufacturing. Look at the way a piece of stamped metal was formed into the first bearing. Look at this load capacity diagram of where the loads are compared to where the balls and the shafts are. How they can be mounted in a pillow block. How a round section can take equal loads from all directions. And notice the arrow's length represent the load capacity, which is higher right over a ball, and the open design. Self-aligning versus non-self-aligning. These linear guides are fantastic, but you know they're not self-aligning. So in some types of high-speed automation equipment where there is flexibility going on, you may want to think about still using a self-aligning ball bushing. Right? So beware of everything has a niche. Learn what machine element exists and what the niche is to be used in, and just always carry this with you when you're doing your analysis of the system, both philosophically and then also detailed grinding the numbers through your spreadsheet. Similarly with linear guides, there are different shapes for the ball to groove contacts, different types of stiffnesses that you can get. You got to go to the catalogs and look for what's the shape of the bearing rail and carriage, the number of balls, how they're recirculating, the type of lubrication that can be provided. In the linear guides, remember, they also have a retainer. The retainer is either nothing, or the separator, excuse me. Spacer balls, or some of the newer guides actually have a flexible polymer belt that keep the balls from touching each other as they're rolling. Just the way rotary motion bearings, the vast majority have a separator as they spin to keep them from the rolling elements to keep them spaced so they don't grind on each other. One of Mr. Teramachi's later inventions was a polymer separator for these linear motion bearings. Earlier, there have been recirculating roller bearings for linear motion that used a retainer. Essentially, what they were doing is they took roller chain and built it into a bearing housing. So the field of linear guides, very well developed. And so remember, for linear motion guides, also F equals Kx. They are so stiff and so strong in general that you either have to provide compliance in your machine, check the loads, or if the machine, big rigid machine tool, precise machining of all the parts to make this small, so given this being big, the load on the bearing is from misalignment is a very small fraction of the load that is the maximum load allowable for very long life. The other aspect of all these linear motion bearings, high speed. Most of the load capacity is defined for a standard of 100 kilometers of travel. High-speed automation machines could use up 100 kilometers of travel in a matter of months. Be very careful to read the fine print. Is this bearing designed for light loads, very long travel, or heavy loads, short travel? There's a difference. There's not one bearing that does it all, because it also will affect the type of lubrication you select, the type of separator, and the mounting condition. In the end, if you don't do this, it'll do you.